Hello, everyone, and welcome to the Bartosagi Labs webinar, where we're going to be talking about single particle cryo-electron tomography and nextPYP. My name's Abby. I'm going to start us off with some logistics and an overview of the agenda before we get into our introduction session. So again, this is going to be the workshop introduction. First off, some logistical points. For questions and answers, you can use the Q&A box to post questions during talks. We're going to have a moderator who will look at those questions and read some out loud for the speaker to address after their talk. Sessions will be recorded and posted after the conclusion of the workshop to be able to look at later. And then for the practical setup for tomorrow, for people who are using the Bartosagi Lab instances, instructions are going to be emailed to participants on how to access those. And then for people who are bringing their own instances, data download instructions should have been available. Right, so for today, day one of our agenda, we're going to start with session one, which is going to be an introduction to nextPYP. You're going to get an overview, which Alberto will introduce you to in a minute. Then you'll talk about the architecture, installation, and user interface, which Jeff Martin will introduce. After that, we'll go into session two, which is going to cover the processing pipeline for Cryo-ET. The pre-processing of tilt series I'm going to cover, and then constrained refinement and classification, Shanfu will talk about. And then the last session of the day today is going to be on-the-fly processing and advanced topics in nextPYP. Live pre-processing is going to be covered by Laura, and then advanced topics and additional features will be covered by Ye. Tomorrow is going to be our practical sessions. For those, we'll have two sessions, and the first is going to cover data pre-processing, starting from raw tilt series and going to 3D particle picking. I will be covering the data import and data pre-processing, and Ye will be covering the 3D particle picking. After that, we're going to do session two, which will cover 3D refinement and on-the-fly processing. Shanfu will cover constrained single particle refinement and classification, and Laura will cover live data pre-processing. And then we'll conclude day two with a troubleshooting and one-on-one assistance for people using our instances. All right, and with that, we're going to start session one, the introduction to nextPYP. And welcome, Alberto.
Great, thank you, Abby, for the introduction. So I'm gonna get started here with giving you an overview of nextPYP. First off, I wanted to acknowledge everybody that's been involved in putting this package together, especially Duke University for allowing us to use this Zoom webinar feature. All the people at the Office of Information Technology that is actually supporting all our computational resources, which some of you will be able to use tomorrow for the practical. And obviously, we're already building a community of users on GitHub. We have provided a lot of useful feedback already that you see that has been transformed into features and improvements in nextPYP. Obviously, a shout out to our research sponsors that actually support a lot of the method development efforts that are going on in my lab. So we're very thankful and grateful to receive that support. I want to start off by telling you a little bit about the team behind nextPYP, and put some faces in here in the order in which you're going to see them in the workshop. So Jeff Martin is a research associate in the lab. Abby, who you just met, is a PhD student. Shanfu, also a PhD student, soon to be PhD next week. Laura, also a PhD student from computer science, and then Yi, who is a research associate in the lab as well. There's many other people. You're only going to see these faces today, but there's many other people that actually contributed to PYP, nextPYP in the past, including Wendy, Wei Sheng, Xiao Chen, Jonathan, and Justin. So it's just like a big team effort, that takes to make something like this happen. So I think, if you're in this workshop, I don't need to introduce or give a motivation speech on, how powerful in situ structural determination using cryo-electron tomography is. I think these are very exciting times, in general for the field. So I'm just going to skip that part. And I'm just going to first of all, before jumping into the contents, I want to tell you what are the things that I'm not going to talk about, or I guess you're not going to be hearing about in this workshop. And that is, this is not going to be like a crash course on cryo-electron tomography. There's great resources in the community for that. So if you're new to Cryo-ET, you may find that there is a little bit of a barrier because we're going to jump straight into the practical aspects. But there's several resources available if you wanted to get some background information on that. We're also not going to talk about sample preparation or data acquisition. There's other webinars or seminars on those topics, which are great resources for the community, but we're not going to talk about that today. And also, we're not going to talk about any specific biological stories. What we will talk about is we're going to focus exclusively on the data processing pipeline for cryo-electron tomography, and in particular, the functionality that is implemented in nextPYP. So you're going to hear about some use cases of the program, and then obviously tomorrow you're going to have the chance to actually do this on our instances, on your own instances, just go through step by step during the practicals. So that's kind of like the plan. I want to start by saying that it's very exciting to see all these technological developments in the field of Cryo-ET that have really transformed the speed at which we can collect data. So the automated 57 million of lamella that can now produce lamellas in an automated manner at high throughput combined with the beam image shift tomography that actually allows you to collect multiple TIL series in parallel, and add to that several efforts that are going on in smart microscopy. You mix all of that together and you get essentially like a sea of data that you can produce very rapidly from this pipeline. And what that actually does, it creates a bottleneck going into the data processing. So one of the things that nextPYP is trying to do is kind of like trying to address that bottleneck that data processing becomes in this context. So just to give you like an overview of what will actually happen after you collect that data is it will go through these several steps through a data processing pipeline, which will involve, if you're collecting movies, you need to align those frames, then you need to align the TIL series. After that, you need to estimate the CTF, and eventually you'll build a tomogram, and you're going to pick particles from those tomograms. So all of these steps are what we're going to be calling part of the pre-processing of TIL series. And just to give you a little bit of perspective, if for people familiar with single particle cryo-EM, each of these steps are actually in a way analogous to single particle, but there's more nuances. There's more things that can actually go wrong. And it's just like a more complex pipeline that you need to go through when you're pushing data through the pipeline. At the end of the day, once you were able to pick particles from your samples, whether it's in situ or purified, you're going to use those particles to convert them into a high resolution structure. And again, this 3D refinement and classification pipeline involves a sequence of different steps, which you're going to get a better idea as we go through today's webinar. Which includes, how do we refine, how do we produce high resolution structures, how do we study heterogeneity using, 3D classification and other approaches, and how do we actually leverage the fact that we have these movies that actually allow us to follow the beam-induced motion, correct for all these effects that are going on as we acquiring the TIL series. So, guess I'm skipping a slide here. So obviously there's multiple different packages in the field that actually allow you to go through all these steps in the Cryo-ET data processing pipeline. I'm listing some of them here. So there's Scipion Tomo, TomoBear, EMAN2, Dynamo, EM Clarity, Relion, Warp-M, StopCap, TomoNet, and the list is probably bigger than these. But obviously there's a big effort from the community as a whole on trying to address this problem. What is common to all of these packages and also to nextPYP is that there are essentially three major challenges that these programs have to solve or have to deal with. First of all, is that because there's so many steps in this pipeline, that just makes it error prone. Essentially, there's more things that can go wrong and probably will go wrong when you're actually doing this when you're analyzing the data. And then the fact that we're actually splitting the dose into a number of tilts compared to single particle cryo-EM, the lower resolution on those frames are going to make it more challenging to align those frames. And then on top of that, you have the tilt series alignment, which you need to make sure that you have enough tracking accuracy during data collection to make sure that you are actually able to align those tilt series. CTF estimation, again, you need to have the defocus gradient, so it's more involved than in single particle cryo-EM. So you have the lower dose and then the focus gradient. So that just makes it more difficult. And then, of course, there is the tomographic reconstruction, which is, has distortions because of the missing wedge and so forth. So when you put all of these things together, there's just like a big chance that things at some point or another are going to go wrong. And you just need, that's just like a big challenge in the field. So the second challenge is that, again, because you have so many steps, there's actually an accumulation of errors that at the end of the day will lead to lower resolution, right? So every step along the way, there is a chance that you will lose some of the information, high resolution information in your data, and that will mean that your final resolution is going to be of lower quality. So you probably heard about this data processing B factor. So essentially, this B factor contributes to lowering the resolution, and it comes from making all this sequence of different processing steps, and that can include cumulative alignments, alignment errors rather. Also, when you do image rotation or volume rotation, you're committing like interpolation errors, and then of course, if you're mixing and matching multiple tools together, you need to deal with this interoperability between packages. So that just makes it really difficult, to streamline this whole process. The third challenge, which is also very important and one that we very heavily focus on when developing nextPYP, is the high computational and storage needs of these Cryo-ET workflows. Maybe the best way to illustrate that is just, give you one example. If you're using like a Falcon 4i camera that produces images that are 4K by 4K pixels, and then if you're taking a tilt series with 41 tilts, and then each tilt has 6 frames, you're talking about having 250 frames for one individual tilt series, which is not doesn't seem that it is that much. 250 micrographs we do routinely in single particle cryo-EM, but that's just only the raw data, right? Then you need to convert that into a 3D tomogram, and then at that point, that 4K by 4K image will be converted to a volume if you're doing like ambient tomogram, which is 4K by 4K by 2K, and then you're talking about 128 gigabytes for a single tomogram. Right? So the data sets that we're collecting today are in the order of hundreds of tomograms. So if you say you collected 200 tilt series, you're going to be looking at 25 terabytes just to store your tomograms. We haven't done any further analysis yet, and you're already looking at these very humongous numbers that just going to take a toll on any storage system that you have available. Once you have your tomograms, then you need to do the 3D single particle analysis, subvolume averaging. And if you're looking at the data set of this size, you probably have like 100,000 subvolumes. And then each of those subvolumes, you have 384 voxels cubed. Then just for storing the subvolumes, you're talking about an additional 20 terabytes. So you can see how this can add up. And we haven't even talked about, now trying to align these many volumes with these volumes of data. It just creates enormous challenges in how do you computationally, are able to analyze this data. And most labs, they don't just work with one data set, they work with multiple data sets. So you can see how these numbers can very easily explode, and they can exacerbate every effort in making sure that you have enough storage available. So If you've done Cryo-ET before, I hope you can relate to all of these three challenges. We suffered through them as well. And nextPYP kind of was born out of how we go about overcoming these challenges. And what I wanted to list here is what is kind of like the philosophy behind developing a package like this. And that's directly motivated by, how do we address these three challenges, right? So the challenge number one, the fact that we have so many steps and things can go wrong. So nextPYP, what we do is we take this is a robust data-driven approach to refinement, which actually allows us to automatically figure out where errors are happening, and then we can do things to fix those problems. But we don't need to be actually looking all the time exactly where the errors are happening. So there is kind of like this robust data-driven approach that helps you automate all of those steps. Second, I mentioned there is accumulation of errors that essentially translates into having low resolution maps at the end. So the approach we took in nextPYP is we just cut through all of that and we do just one step from raw data to 3D reconstruction. And that's the high resolution 3D reconstruction. So by eliminating absolutely every step in between, we just do one step. So then there's no loss of high resolution information. And that's something that it works very, very effectively. Last but not least, as I said earlier, we spend a lot of time making sure that we could overcome these barriers that are related to storage and compute capacity. So the way we address that in nextPYP, we actually leverage like this modern HPC infrastructures, and I'm going to give a little bit more detail about that. And also, we're going to address this bottleneck of having enough storage to be able to, analyze data sets of the magnitude that today's microscopes are actually producing. So this is kind of like an overview. So kind of like the introduction of nextPYP. This is, it's a scalable, and I'm going to go through each of these terms one by one. So it's a scalable end-to-end platform for single particle Cryo-EM and Cryo-ET image analysis. So you notice that I said Cryo-EM and Cryo-ET. So this webinar, we're only going to focus on the tomography part, but for people that are curious, this also nextPYP also supports pretty much all the same operations for single particle Cryo-EM, but that's not going to be the focus of today's workshop. So essentially, this the package will allow you to process your data on the fly as you're collecting in the microscope, all the way from analyzing the raw frames to producing particles that may be ready for 3D refinement. It has a complete suite for particle picking that allows you to pick particles using different strategies from different samples, and then also has several components that allow you to actually refine your data to high resolution using a variety of different methods to actually get to high resolution structures from your samples. I want to go over some of the main features of the package. As you will see, this is a portable tool that includes like a fully featured web-based graphical user interface. And in addition to that, nextPYP also provides a command line interface for those of you who prefer the command line. And essentially, there is like an end-to-end pipeline that allows you to go from raw data all the way to 3D reconstruction. One of the things that we're most proud about of nextPYP is the fact that it has like a very small storage footprint, which essentially won't completely kill your network storage or your local storage. And I'm going to tell you a bit more about that in a couple of minutes. In addition, it also has a distributed processing architecture, which allows us to actually scale the data analysis to very large data sets with potentially thousands of tomograms. It used to be that data sets of that size, we couldn't possibly do in a reasonable amount of time, like not very long ago. But adopting this distributed processing strategy, we can actually manage, very, very large data sets and it's actually quite fast. And you're going to see some of that yesterday during the practical. If you attend that, you're going to see how that works in practice. Last but not least, nextPYP is free and open source software. It's all available on GitHub. And the code is licensed under the BSD 3 clause license. So that's kind of like the overview of all the features. So now we're going to go into each of these components fairly quickly. So portability, I think everybody can acknowledge that what web browsers can actually do today, and the powerful applications that you can run, and just the convenience of being able to to access this application from any device that you have available. It has, at least for us, it has really made a change in the way we interact with data processing, and also with the getting feedback during data collection. So as I mentioned, this is like an end-to-end pipeline, and you're going to see more details during the rest of the workshop today. But essentially, this is showing like you start on the left from your raw data, and then you go through different hopes of steps of the data processing. And once you get to the right, you have your high-resolution structures, and you can do all of that within the web browser without ever having to go out and do things separately. As I mentioned earlier, we're actually very proud of the storage footprint of nextPYP and how it leverages the distributed computing. And just to give you a sense of where the storage savings come from, we don't ever build unbinned tomograms, right? So we only build heavily binned tomograms, are only for specific purposes. So those are actually very small files. We don't ever create a sub-volume where we're doing 3D refinement. And also, we don't ever save a single particle stack, right? So that hopefully gives you an idea. That's actually going to save you a whole lot of space, and it will just allow you to process multiple data sets without having to worry about storage, which it used to be a nightmare not very long ago. Then in terms of the compute, obviously, this is not single particle Cryo-ET is not something that you can do like on a laptop, on a local machine. So we actually leverage these newer, high core CPU architectures to be able to speed up and make things more efficient. And in addition to that, to take advantage of the fast I/O of these SSD drives. We combine those two things to be able to get the processing to be very quickly and very efficient in terms of the storage and computing. So you will see that there's a lot of visualization tools that are incorporated into the software that you can just access directly from your browser. That includes tools for T-series pre-processing, but also 3D refinement, including looking at 3D volumes. And again, you're going to learn more about these features through today's workshop. So we didn't start from scratch. Obviously, here we're building on amazing work that has been going on in the community for a while. And in particular, nextPYP builds very heavily on iMod and also system for the 3D refinement part. And we're also trying to incorporate like external pieces of software to the workflow. We recently added Topaz, Motion Core 3, Artomo 2, some examples. But just want to acknowledge that this is not something that we built completely from scratch, but we're actually building on top of these amazing tools that the community has produced, both in single particle and also in tomography. So the main technique under the hood that actually drives the 3D refinement is in nextPYP is this constrained single particle tomography, which essentially does away with producing sub-volumes, because that has many different problems that I'm not going to go through. But essentially, this is the way most packages for high resolution refinement actually work these days. You go directly back to the raw data, your raw 2D projections, and then you remove all the intermediate steps, and then you just impose the geometric constraints that come from tilting your sample, and you can essentially recast the entire subvolume averaging problem as within a single particle framework, and that automatically allows you to leverage all those tools that have been developed and perfected for so long. So everything regarding 3D refinement and actually classification is built on top of constrained single particle tomography. So just to give you some examples of once that framework is in place, you can improve your tilt series alignment. You can improve your particle alignment, and this is all based on the particle data itself. It's not based on fiducials or any other markers. It's based on the individual particles. We also recently incorporated region-based refinement, constraint classification, per particle CTF refinement. Also, we're able to refine individual frames of movies for individual particles. And we can also do exposure weighting, which is actually also based on the data. So just to give you like a sense for this, why is scalability important? And this is an example that where you can see I'm showing like 6 tilts of a tilt series, and then within each tilt I have a number of frames. So those are the dots here. And what we're actually able to do is we're actually able to measure the contribution of individual frames of each of those tilts and actually recover this characteristic curve that kind of like you start low and then the signal, high resolution signal components increase. And then eventually, radiation damage sets in, and then you go back down. And then once you go to the second tilt, you actually see the same behavior, and each successive tilt will actually lower the contribution to high resolution. But the fact that we can do this, we have this scalable framework actually allows us to do things like this on even very large data sets. And then using that, this particular set had 328 individual frames. So we can actually use those frames to make up the reconstructions. And what that means is that you'll typically be doing reconstructions in the tens of millions of individual frames. So having this scalable platform actually allows us to do that quite effortlessly. When you piece together all of these components, you can really squeeze out all of the high resolution information that is present in the data. So here, you start from a baseline, and then as you start to turn on all these features for high resolution refinement, you start getting better and better resolution. We also validated the pipeline using two series of apoferritin, and we were able to get to sub 2 Armstrong resolution using TIL series. This is a data set from Empire database that has about 100 TIL series and 32,000 particles, just to give you a sense for the scale of these numbers. As I mentioned, we're also using 3D classification to study heterogeneity. The example you're seeing here is for native ribosomes, 78 ribosomes on intact cells. And this is from the Empire database 10499, where we can actually tease out different conformations and piece together the different states of translation of the ribosome. In addition to the data processing pipeline, we can also do on-the-fly data analysis, and you're going to hear that today, and you're actually going to see it in action tomorrow. But you can be running nextPYP as you're collecting the data, and then you can be getting feedback on whether your TIL series are good enough to be aligned. How far does your signal go? Do you have enough particles? So all of the information that you typically get in single particle, you can also get it in tomography. And as I mentioned earlier, nextPYP can do both. So the same interface you can reuse for either one modality or the other. So if you're only going to be here for the webinar and not the excuse me, and not the practical, we set up this live demo website. So you can just go and log in. It's called demo.nextpyp.app. And this will actually allow you to navigate an instance of nextPYP. So we populated it with a couple different data sets so that are actually part of the tutorials of nextPYP. So you can go in and you can click to the interface and you can get a better feeling, what this looks like. So that's all available if you want to take advantage of that. Getting to the end here, I do want to mention, excuse me, do want to mention that, one sec. All right, sorry about that. Everything that I went through today is covered, in a number of publications spanning, more than 10 years, going back all the way to 2012 when when we introduced the constraint particle tomography paper. So the main program, the nextPYP, was described for the first time in a paper last year, which is the first reference here, but then all the others are actually, incorporated into nextPYP as well. Okay, so that's pretty much everything I wanted to say for the intro, and I do want to leave some time for questions. But before we do that, I just wanted to give another kind of like reiterate on what Abby went over for what's going to be the plan for today and tomorrow. So you're going to be hearing in quite a bit more detail in what's the architecture of the software, how do you go about installing it, what kind of resources you need to run, what are the components of the graphical user interface. And then we're going to focus on the different steps of the data analysis, starting with the pre-processing. Then we're going to transition to talking about high resolution refinement and classification, followed by the on-the-fly live data processing. And then at the end of the day today, we're going to talk about some advanced topics and additional features that maybe you may find useful. Tomorrow, you're actually going to get a chance to get on the driver's seat and convert raw movie frames from tilt series, and then be able to convert that all the way to 3D structures. I'm going to be using multiple different data sets so you can test out different particle picking strategies, different strategies for T-series alignment and so forth. And we're also going to demonstrate how you run a session live during data collection. One thing you will see is that at some point tomorrow during the practical, you're going to be able to produce a reconstruction from about more than 3 million projections. So you're going to see how that scalability comes into place, and what are the savings in terms of storage and so forth. So I'm gonna stop there and leave time for questions.
All right, so we do have one question in the Q&A for you, and it's, can we run on GPUs or do we need CPUs? And then, well, there's a follow-up to that, but maybe hit that one first.
Yes, so originally nextPYP was actually designed to exclusively run on CPUs, and you can actually go all the way from beginning to end just using CPUs, provided that you have enough of them. None of the native code in nextPYP has been ported, to or can take advantage of the GPU. So I guess the question is, it's designed to be used on CPUs. That being said, these days you can actually get servers that can have a lot of cores in the order of hundreds. So that can actually be useful to get you started. The other thing that is relevant here is that some of these other packages that we recently incorporated, like Motion Core 3 and Artomo 2, they do run exclusively on the GPU. So if you wanted to run those programs, you need to make sure that you have access to GPUs. But everything can be done exclusively on CPUs, and it has been heavily optimized to use that type of architecture. Was there a second part to that?
Yeah. Another question from Luis was, what is the optimal way to collect data? For example, should we use bisect?
Right. So I did say at the beginning that we're not going to talk about data collection because that alone can take up like an entire workshop. But what I do want to say here is that like a framework or a tool like this, one of the things that it will allow you to do is will allow you to actually tweak your data collection parameters, right? If you wanted to like reduce the number of tilts or increase the tilt spacing, or just collect a couple of images as opposed to 41 images. So a framework like the one that we built in nextPYP would actually allow you to analyze data collected under any of those conditions. The reason that's I believe it's important is that it will allow you to explore that axis, right? So, not too long ago, we went for just plus minus 60, 41 tilts, and we didn't even think about it. We just went with that because we knew how to analyze that data. Now, having this like more generic tool actually will allow you to explore that axis of data collection conditions and be able to optimize that to the sample that you're looking at. Whether you should use bisect or not, I think if you can, you should, unless you have unlimited access to microscope. So bisect will actually allow you to get a lot more data per microscope hour. So if your sample supports that and you're set up to do it that way, you should definitely use that because you'll get a lot more data per session.
Nice. All right. So I'm going to skip over Stavros for now because I think this might be a better question for the next talk. But for Jacob, how is the software able to get around saving particle stacks?
Yes, that's a good question. There is kind of like a caveat. We do produce the particle stacks temporarily, and you're gonna see more details about that later today. But we don't need to save them, permanently. So what that means is that you may have like a little, some bursts of, usage of your data storage, but this will only happen, in the compute nodes. So you won't ever see these, on your permanent storage. It will just happen, temporarily, and once you're done using that, it will just get deleted, and you won't see, usage of the storage go away.
All right. Okay, next question is from Asa, and this is, have you optimized nextPYP on specific high computing architectures, specifically thinking about Intel versus AMD CPUs?
Yes, so we've done some effort to, in general regarding to optimization, right? So CPU optimization. Nothing that is specific to the architectures other than just using, like the Intel compiler and, just building on top of the system code that has been heavily optimized for, for the CPU architectures. So that being said, we do run this routinely on Intel and more recently on AMD platforms. And, I guess it can always be faster and better and and more optimized and specifically to these architectures. But we haven't done like, the very, very fine tuning, that will probably allow you to get the most out of these chips. But again, I think we can't complain about having to wait for so long that that this will become like a very high priority. But yeah, I guess to answer the question specifically is we're not deliberately optimizing for one architecture or the other, but other than just doing like using the proper compiler and so forth.
All right, we're gonna do one, possibly two more. The next one is, are we picking subvolumes from binned tomograms? And then at what stage could people potentially go back to original tomogram for subvolumes in context?
Right. So yeah, you're gonna hear a lot more about how the different steps work together in the pipeline. But yeah, so the picking is done on very heavily binned tomograms, and it's all being done through the web interface. And then once you go and start producing 3D structures, at that point you will always be going back to the not to the original tomogram, but you will be going back to the raw tilt series, right? So every 3D volume that comes out of nextPYP is going to be produced straight from the 2D projections. So you altogether skip the generation of the unbinned or original tomogram.
All right, and Ryan asks, in the current version, is it possible to save temporary particle stacks and write out corresponding metadata?
That is not currently possible. It's on our list of things to do because we realize that if you want to do something like outside of nextPYP, you are going to need particle stacks. But yeah, unfortunately, we have it on our list, but right now the current version it will only save it temporarily. So once it's done, finished, you won't ever see a particle stack. We do, the metadata will already be there, just that the particle stacks, they won't show up on your file system.
Oh, right. All right, and I think we have time for one more before we transition over to Jeff. And what we're gonna take out of the many good questions here, a lot of the questions are about environment, and I think Jeff is gonna answer that for you guys, so I'm not ignoring you. But okay, so one would like to know about Motion Core 3 and RTOMO 2, I guess why we're incorporating those. Have they been tested before being added to nextPYP?
Yeah, I'm not sure if this refers to those packages themselves having been tested or within the context of nextPYP. So those are two examples of user requested features, and as far as we know, they work well. That's the reason why people requested that, and we also confirmed that they're doing what they're supposed to do within the context of nextPYP as well. So I guess in that sense, we have done that testing. It's not part of our main pipeline, mainly because when you use these packages, you need to have access to GPUs. And then the scalability there is not as good because normally there's a lot more CPUs than there are GPUs. But they should be, they should do what they're supposed to do when you're running them from nextPYP.
All right. Thank you, and I think we're out of time for questions for this session. Yeah.
Thank you, Abby.